introduction to this topic of quadratic residues. So we're going to continue with it today. So just to recall the definition, definition 8.1. So P is an odd prime number. When we say P is an odd, when we say odd prime, we mean a prime different from 2. Okay. So P is an odd prime number, and let n here. Is it gone, is it? Right. Well, let n be an element, so we just focus on elements of the multiplicative system modulo p. So, i.e., p does not divide n. Or another way of saying is that n is not congruent to 0 modulo p. Remember, ZP, multiplicative system mod p is all the non-zero congruence classes mod. And if there are solutions, x to x squared being congruent to n modulo p, then we say n is a quadratic residue. Full phrase is n is a quadratic residue modulo p, because it's with reference to the modulus p. Being a quadratic residue is having a square root. Okay. Although in the subject number theory, when we're talking about things, we tend not to use the phrase square root. We tend to talk about being a quadratic residue. Otherwise, you're a non-residue. That's when there's no solutions x. N is a quadratic non-residue. On P. We looked at several examples yesterday. The first few odd primes. We looked at P equals 3, 5, 7, and 11, I believe. We looked at all the congruence classes with respect to those moduli, and we just investigated which ones were quadratic residues and which ones were. We found, well, we noticed a few things. We noticed in those few examples that we looked at that half of the non-zero congruence classes seemed to be residues all the time, and half of them didn't. We saw that, well, of course, anything that's a square integer, such as 1, 4, 9, 16, anything that's obviously a square integer is, of course, going to be a quadratic residue, because you already know it's going to have a solution x. The solution x, of course, it's implied that it's coming from the same set. So if something is a square integer, it's clearly a quadratic residue, but other things can be quadratic residues as well. Modulo p. And then I started to look at, which we'll talk about in a minute, how the quadratic residues and non-residues might behave like positive and negative numbers. And we'll see that for definite later today. So any questions about the definition, first of all? If you weren't here yesterday, I do encourage you to look at the lecture recording from yesterday and to spend some time looking at those early examples. Clarify. So our first theorem, theorem 8.1, proves that observation that half of them are residues and half of them aren't. So this is about counting residues. So we let P be an odd prime. Just have that as a general assumption in the whole chapter. P be an odd prime, then of the elements in ZP, so remember this is all the congruence classes from 1 to P minus 1. Of these elements, half are residues, half are not. P minus 1 over 2 are residues, and the other half are not. Half of them are residues, half of them aren't. P minus 1 of these things here, P minus 1 is an even number, so P is an odd number. So P minus 1 over 2 is half of it. Now we saw this happening in the examples, okay? When we looked at P equals 3, 5, 7, and 11, we saw this. So we verified, we've already proved the theorem, P equals 3, 5, 7, 11. Here we want to prove it for every odd prime. The proof is fairly straightforward. We begin by immediately pointing at what the residues are. So we consider the elements of ZP represented by 1 squared, 2 squared, 3 squared, all the way up to P minus 1 over 2 squared. Why have I stopped there? Why don't I continue? This only goes halfway along the list. Why don't I continue? Somebody made this observation yesterday. Looking at the congruence classes represented by these numbers here, square root of 1, square root of 2, square root of 3, etc. Square root of 2. Well, see, I don't need to go any further because if I went, so this is the halfway point along here somewhere. If I went further, I mean the next number, which is P plus 1 over 2, that's the negative of P minus 1 over 2. So when you square it, you get the same congruence class as this. When you square a negative, you get the same congruence class as the square of the positive version. And the next number after that is the negative of the next one here. You know, finally, this last one, P minus 1, is the negative of 1. When you square P minus 1 is congruent to minus 1, so when you square it, you get the same value as 1 squared. That must be 1. So if I go any further, I won't be getting any new elements. I'll just be getting just these. So clearly these are all residues. Because they're all explicitly given as the square of something. Remember, the residue, a residue is something which is a square. These are all explicitly presented as squares. So they're definitely residues. These are all residues. And all the residues are listed here. This is this point about the positives and negatives. Because if J is if J comes from the second half, so if J is from P plus 1 over 2 all the way up as far as p minus 1. J is one of the numbers in the second half. And j squared, which of course will be congruent to minus j squared. But minus j will be congruent to p minus j squared. Roll mod p. And p minus j will be on this list because p minus j will be between 1 and p minus 1 over 2. J comes in the second half of the list. Yeah. P minus j, the distance between j and p, will be from the first half of the list. And if you're wondering what j squared is, well, it's going to be congruent to minus j squared. So that's going to be congruent to p minus j squared, because p minus j is congruent to minus j. But that's already listed here. P minus j squared is already listed here when j comes in the second. So these are all residues. They are all of the residues. Still one subtle detail we want to prove to justify the claim that half of the elements are residues. And that is to prove that these are all distinct. Yeah? There's what, if you count these, there's 1, 2, 3, p minus 1 over 2 of those. But we just need to be sure that they are all distinct modulo p. Could it be that a couple of them are congruent to each other? A couple of the squares are congruent to each other. We just have to settle that point. Finally, we need to prove that all the elements in this list star here are distinct modulo p. They're certainly distinct as integers, but distinct congruence classes modulo p. Well, there's a couple of ways to do this. One way to do this, and it's slightly different from the way that's presented in the notes, is we could appeal to Lagrange's theorem. It says that this quadratic x squared congruent to j squared mod p has only 2 solutions. The general form of Lagrange's theorem says any polynomial modulo a prime, the degree of the polynomial is an upper bound on the number of solutions. So a quadratic polynomial has at most 2 solutions. And because it's a special one, it's congruent to j squared. Well, we know it has solutions, j and minus j. But it can't have any more than 2 solutions by Lagrange's theorem. Namely, x congruent to j or minus j modulo p. So minus j, that second one. J and minus j. So that means here's our j, here's 3 squared. Well, there's only 2 things that square to 3 squared, namely 3 and minus 3. Well, minus 3 hasn't been listed here because minus 3 congruent to p minus 3, that's in the second half of the congruence class. So we haven't listed that. This proves star are all distinct. I.e., there are p minus 1 over 2 quadratic residues. And there's a more explicit direct argument given in the notes, which kind of does proof by contradiction or whatever. It assumes two of these are congruent, then argues that it must be just looking at the same thing twice. But I think that's quite a good efficient use of Lagrange's theorem as well. So that's really good. That means we've proved that conjecture there that we formed from the examples yesterday. Okay. Okay, any questions about that or clarification I could give on that? All right. So, in real arithmetic, positives have square roots. Negatives don't. That's something you're familiar with, just in real arithmetic, normal multiplication of real numbers. We recognize the things that have square roots, they're positive numbers, negative numbers don't. Now remember, before yesterday or before, up to now, we don't have a notion of positive things and negative things within the modular arithmetic because everything can be simultaneously a positive and a negative because every congruence class has an infinite number of elements in it, positive elements and negative elements. But maybe the important thing here is not whether something is positive or negative. Maybe that's not the primary thing. The primary thing is having a square root or not having a square root. So maybe the residue, non-residue distinction that P, multiplicative system modulo P, operates in the same way as the distinction between positive numbers and negative numbers in real arithmetic. And what do I want to say? Works the same way or mirrors this? Now, what do I mean by mirrors this? Well, one specific way is what happens when you multiply residues and non-residues. From the examples we looked at yesterday, we formed a conjecture. This conjecture had three parts, and it mirrors the way that you're familiar with multiplication of positive and negative numbers works. So what happens when you multiply two residues? What happens when you multiply a residue and a non-residue? And what happens when you multiply two non-residues? So what's the classification of each of these products? Well, if it's going to work, if it's going to mirror the positive and negative behavior, having a square root, not having a square root. Residues have square roots. If you multiply two residues, what we saw in the examples and what we conjecture is going to be true in general is that you get a residue. When you multiply one of each, you multiply a positive real number and a negative real number, you get a negative real. And what we saw in the examples and what we think might be true in general is that we're going to get a non-residue when we multiply a residue and a non-residue. Okay. And then finally, when you multiply two non-residues, well, it's going to work the same as positive and negative numbers. You know that when you multiply two negative numbers, you get a positive. So we're going to expect to see a residue when we multiply two non-residues. We know it's true for p equals 3, 5, 7, 11. Just inspected it. Direct. Well, we don't necessarily know, but we checked some examples in p equals 3, 5, 7, and 11. And we saw that it was true. We could have exhaustively checked all possible pairs. We would have seen that it's true. Well, how might we prove it in general? So we need a proof of this. Now, this isn't in the notes. Well, it kind of is in a later. It's actually most of theorem 8.3, but that requires some new notation. Well, I think we could prove this. I think we could prove this right now. Yeah, without too much difficulty anyway. So let's try and prove these. So we have to let p be any odd prime number. So we don't have a specific. So let's take case 1. So we'll let u and v, what do I call them? U and v. Let u and v be residues modulo p. I want to prove that the product is a residue. How do I prove that the product is a residue? Can I convince myself or others that this is that this will be true? So I've left a gap. The gap isn't too big. You can either try and push your assumption forwards or draw the conclusion backwards.
The residue UV squared must have an answer to modulo p.
Say it a bit more precisely. So what has a solution?
So if u and v are residue, then
Yeah.
UV squared must be residue as well.
Well, it's not u. So we're not talking about u squared and v squared.
No, u.
No, I think you're right. So u and v are residues. That means when you square something else, you get u. That's the point. U has a square root. So there is something else out there that when you square it, you get u. And similarly for v. That's what being a quadratic residue means. Yeah? It's not talking about u squared or v squared. It's talking about the square of something else that gives you u. Yeah. So i.e., so this implies there exists an say an alpha and a beta, Zp. If you square alpha, you get u, and you square beta, you get b. Or let's say congruent. Yeah. That's the definition of being a quadratic residue. You are the square of something. So how do we know u, the product uv, is a square?
Alpha squared b squared is congruent to something.
Congruent to what? Has to be uv, yeah. Because uv is congruent to alpha squared, beta squared, and how would you organize that? Trivially, kind of to emphasize the point. We're not yet looking at the square of something. We're looking at two squares multiplied together. So is that a square? Maybe you already see it in your mind. Yes, it's the square of a alpha beta. Yeah. Yeah. So that proves that U times V is a residue. Yeah. Because it is the square of something. Something that it's the square of is the product of the two square roots of V. So yeah, if you take two residues and multiply them together, you do get a residue. Just like when you multiply two positive numbers together, you get a positive. So part one of the conjecture is true. Can we go for part two? So what do we say for part two? We say let U and V be elements of ZP. Let U be a residue and V a non-residue. So the U, i.e., U is the square of something. But V is not. And down here, I want to conclude that the product U times V is a non-residue. This is like multiplying a positive number times a negative number. You know you get a negative number. But here, we're multiplying something that has a square root by something that doesn't. And we want to conclude, therefore, that the product does not have a square root. Just notice it's not as nice a kind of setup. The previous one was very open for just a direct proof, because the assumption was the assumption is quite a positive type of assumption because it tells you about something that exists. U and V are residues, so there is this thing called alpha, there is this thing called beta with special properties, they square to U and V, respectively. And the conclusion we had to prove was of a very similar nature. That UV has something that when you square it, you get U. You're able to build the proof quite directly. This one is slightly more harder to get a hold of because, okay, one of the assumptions is a similar positive assumption. U has a square root. U is a residue. But the other one is kind of negative. V does not have a square root. It's a non-residue. And that's kind of awkward because it doesn't immediately give you something extra, an ingredient that you can use. It's a kind of a negation of something. It's slightly harder to get a hold of. And the conclusion we're looking for is this kind of negative type of conclusion. So we might need a different kind of way of approaching this proof, a less direct way. What might that be? Proof methods. Do we have to try and prove something, but we come at it at an angle, kind of not head-on, direct proof? Kind of a trick, or it's kind of a. Proof by contradiction. Contradiction, yeah. So how do we start a proof by contradiction?
Assume the opposite of what we're trying to prove.
Okay, which is?
That UV is residue.
Yeah, yeah. Assume, for contradiction purposes, that UV is a residue. I.e., so what are you assuming? More explicitly.
I can restatement of what we had in one, where saying that U times V. Can we write U?
Yeah, can be written as a square or something.
Yeah.
Yeah. And we don't yet know that it has any relation to alpha, but just using the definition, i.e. uv is the square of something, beta squared for some beta in zp. Okay, that's good. Now we've got an extra ingredient. We've got a beta. We know there's an alpha floating around. Now we've pretended there's a beta floating around. Now, what's our aim now? Given that we're into a proof by contradiction, what are we aiming for? Yeah. What kind of a false statement are we going to be deriving? What are we going to contradict?
Assumption.
Which assumption? That U is a residue? Or?
UV.
Well, we just assumed UV is a residue. We're not going to contradict ourselves straight away. We're going to, that V is a non-residue. This is the thing we're going to contradict. Because remember, we've assumed V is a non-residue. But if we somehow simultaneously now prove, but V is a residue, then that's our contradiction. V can't be a non-residue and a residue. It's either, it's this or that. It can't be both. So so the contradiction that we're gunning for is to contradict this assumption that V is a non-residue. How do we contradict that? How do we go? Well, we can't just say it. How do we contradict that V is a non-residue? So, proofs by contradiction finish by saying this is a contradiction. So that leads us to say that what we assumed here was wrong. So that gives us the desired conclusion. The thing we're going to contradict is we're going to somehow say V is a residue. The only way we can say that is if we see that V is the square of something, not P. This is how, examining your argument gives you, so this is what we have to do now. We can find an element to put in here. That's when you square it, you got V. That would prove V is a residue, but that would contradict the fact that V is supposed to be a non-residue. What's the blank? What goes in there?
Where the residue.
No. Clearly, you said some very relevant words, multiplicative inverse. So what goes inside the bracket? V is U inverse times U of V. Yeah. U inverse and U cancel. V. UV we know is beta squared. And what's U inverse? How would you express U inverse, the inverse of U? U to the minus 1, okay. No, it's not minus, no. The additive, multiplicative. Well, I mean, you can say it's U is alpha squared, so it's the inverse of alpha squared. So just use your rules of indices. Power of a power is the new exponent is the product of those, so you can just reorder those. bring the square on the outside, so it's alpha inverse on here, isn't it? So it's alpha inverse times beta, where alpha inverse is the multiplicative inverse of alpha modulo p. These are all congruences. Congruences modulo. So suddenly you're looking at V being the square of something. So V is a residue. But that contradicts the fact that we told ourselves that V was a non-residue. So something's gone wrong. We can't have V both being a residue and not a residue. So what went wrong was we assumed here, for the purposes of contradiction, that UV was a residue. So the conclusion must be that under these assumptions here, under those assumptions there, these give us that UV is a non-residue. Can't be a residue because if UV is a residue, with these assumptions, you get a contradiction. V is both a non-residue and a residue. So that's good. Residue times non-residue gives us non-residue. Just like positive times negative gives you negative. In real arithmetic. So we still got to do 3, where we say let U and V be non-residues. And the conclusion we want is UV is a residue. Now this is maybe a little bit harder because both of the, the whole assumption now is a kind of a negative one. There does not exist square roots of these two numbers. But we're trying to prove that UV does have a square root. So this can't be proved. This can't be proved in the same way that we proved 1 and 2. I think. Contrapositive. Okay, so what's the contrapositive?
So if UV are non-residues, then U and V are residues. Not P, they're not residues.
Yeah, so you didn't say it quite right. You almost said, so the contrapositive would be UV is a non-residue, implies it's not the case that they're both non-residues.
Yeah, they're residues.
No, but no. The negation of this is they're both residues, or one is a residue and one isn't, or vice versa. So there's actually three subcases, or at least 2 subcases there. So, but then you're trying to, the conclusion you're trying to get is multi-pronged, so that's doesn't seem immediately easier. Yeah. Yeah, because this is like an and statement. U is a non-residue and V is a non-residue. So not that can happen in multiple ways. So doesn't seem quite as straightforward as the previous cases. We need something more. But we have done something more, because earlier today we proved our theorem about counting the total number of residues. We've already seen that there are half of the elements are residues, half of them aren't. So let's say let R1 up to Rp minus 1 over 2 be the residues. We've already shown that when you multiply U with one of these Ri, so that's a non-residue times a residue, that was part 2. We've already proved that this is a non-residue. That's by part 2. But the Ri's are all the residues, and there's P minus 1 over 2 of them. We've already shown that each of these products, U times Ri, remember U is a non-residue, but these are all non-residues. This gives us P minus 1 over 2 non-residues. You got UR1, UR2, all the way up as far as UR to the P minus 1 over 2. And just to emphasize that, these are all distinct. I said there are P minus 1 over 2 non-residues. There's definitely P minus 1 over 2 things written down here. Count 1, 2, sorry, P minus 1 over 2. And they're all distinct. None of these two things can be congruent to one another because you can just cancel the U's. If URI was congruent to URJ, that would imply that RI is congruent to RJ by multiplying both sides by the inverse of U. And by implication, these are the distinct total list of residues. Right? But how many non-residues are there? We know there are exactly P minus 1 over 2 non-residues. So we've used them all up. We've accounted for them all with these products. So U times V is a non-residue. So V is not one of these things. So U times V must be another kind of element. Slots for all the non-residues are already occupied with these products. U times V has to be something else. We've run out of room. The product UV, this V is still covered by this assumption up here that V is a non-residue. It must be different from any of these. Again, it couldn't be congruent to one of these because you could cancel the U's. And then the V would have to be congruent to one of the R's. The R's are all the residues. V, we said, is a non-residue. So the product UV must be a residue. That's by theorem 8.1 and accounting argument. There's only P minus 1 over 2 non-residues. Here we've indicated them all. These are all distinct. So what is the product U times V? Can't be a non-residue. That would mean it would have to be congruent to one of these. But then V would have to be a residue. You cancel the U's. So there's no other possibility. Everything's either a residue or not. So UV must be a residue. Ruled out the possibility that it's a non-residue. So that gives us our conclusions. We needed a little bit extra. We needed this counting argument that we'd already experimented on. So that's a further conjecture there that we started to see or started to suspect from looking at our examples that we've now proved. Being a residue, being a non-residue, does have the same multiplicative structure as your positive and negative real numbers under multiplication. So it gives us further insight into this. Okay, now as you can see from glancing through the chapter, we've got a few substantial results to get about. There's still a lot of kind of mystery here. Just about the general question, if I name a large prime and name a congruence class moduli of that prime and ask you, is it a residue, is it not? Still don't have many tools, apart from just trying all possible squares. Still faced with, how do you work out if something is a residue or not? Still need some better, efficient methods for that. And that's what we're going to be investigating through the next lecture. Okay, so thanks for your attention. We'll leave it there for today. See you next time.